Railway tracks run through almost every city in the world, cutting across roads and neighborhoods on their way to somewhere else. If you've ever walked across the tracks at a crossing or glanced over while driving parallel to a railway line, you've seen what's underneath those steel rails. Millions of grey rocks, rough and jagged, spread out for as far as the track extends. It doesn't matter if it's a modern bullet train line in Japan or an old freight route in India or Europe. The rocks are always there, but why do we rest trains weighing millions of pounds on loose piles of stone instead of solid concrete? The answer protects the train from sinking into the earth and connects modern railways to ancient sailing ships in a way you wouldn't expect. A loaded train is incredibly heavy in ways that aren't immediately obvious when you see one passing by. A single freight car can weigh 200 tons when fully loaded, and a typical freight train might have 100 cars or more, which means 20,000 tons concentrated on two thin strips of steel. The weight pressing down on any given section of track can exceed several million pounds. If you place that much weight directly onto the ground, the intense pressure would crush the soil and compact it under the load, creating depressions and uneven surfaces that would cause the tracks to sink and buckle until the train derailed. Even a small dip in the track becomes dangerous at high speed, because what looks like a minor settlement can throw a train off the rails when it's traveling at 100 kilometers per hour. The rocks, which engineers call track ballast, solve this problem by working as layers stacked on top of each other. The steel rails sit on horizontal beams called sleepers or ties, and the sleepers sit on the ballast, which acts as a cushion that takes the immense concentrated weight of the train and spreads it out over a wide area so the pressure gets dissipated before it reaches the ground underneath. What makes this work is that the tracks aren't actually fixed to the ground the way you might expect. If you look closely at a railway line, you'll see the tracks are floating on the rocks rather than being bolted into the earth deep below. They rely on friction and the sheer weight of the ballast to stay in place, and this flexibility allows the track to slightly absorb the vibration of a roaring train rather than snapping under the tension the way a rigid structure bolted to solid concrete eventually would from constant vibration. If you picked up a piece of track ballast and held it in your hand, you'd immediately notice how sharp and jagged and rough it feels. These rocks will hurt your hand if you grip them too tightly, and there's never any smooth round pebbles mixed in with them because of how the system works. Imagine stepping into a pit filled with ball bearings or smooth marbles and trying to walk across without sliding everywhere. Smooth rocks roll over each other the same way, so if a train went over smooth round rocks, the vibration would cause them to roll away and the track would slide apart. Engineers prevent this by using crushed stone, usually granite or quartzite, that has been deliberately smashed into sharp angular shapes that interlock when packed together. Their sharp edges bite into each other and create a solid immovable mass that still allows for a little bit of flexibility, locking the track in place and preventing it from sliding side to side even when a high-speed train screams around a curve. The interlocking works because of geometry, with each rock having multiple points of contact with the rocks around it, and when force pushes down from above, those contact points press harder together. The rocks also need to be hard enough to resist crushing, because when millions of tons of train pass over them year after year, softer rocks would literally grind into powder, which is why granite and basalt are preferred for their ability to take the punishment without breaking down quickly. Early railway engineers in the 1800s tried everything else first before settling on crushed stone. Some attempted to lay tracks directly on compacted earth, which worked fine until the first heavy rain turned the ground to mud. Others tried wooden planks as a foundation, but they rotted within a few years and attracted termites. A few experimental lines used brick, which cracked under the weight and cost a fortune to replace. The engineers kept coming back to loose stone because nothing else could handle the combination of weight, vibration, and weather. Water and weeds are constant threats to railway stability in ways that might not be obvious at first. If we laid tracks on a solid concrete slab or just bare dirt, heavy rain would create serious problems because dirt turns to mud, which washes away and leaves the track unsupported, while concrete creates puddles that rust the steel rails and, in freezing weather, form ice on the surface that makes the tracks dangerously slippery. A pile of rocks is perfectly porous in a way that solves all these problems at once. When it rains, water flows instantly through the gaps in the rocks and away from the track, keeping the ground dry and solid because the entire track bed acts like a giant drainage system. If you watch a railway during heavy rain, while the roads flood and fields turn to mud, you'll see the train tracks stay dry because water disappears into the ballast within seconds. And this drainage happens passively with no pumps or drains or maintenance required. The gaps between rocks also allow the ground beneath to breathe because soil needs air circulation to stay stable. And if you seal it under concrete, moisture gets trapped and causes the ground to become unstable over time. Plants rarely manage to grow in the middle of a train track because the thick layer of sharp rocks makes it incredibly difficult for them to take root. And this matters because if plants were allowed to grow, their roots would break up the soil and ruin the stable foundation, since some plants have roots strong enough to crack concrete and would destroy a railway line within years if left unchecked. The rocks act as a natural weed barrier without any chemicals or maintenance because seeds can't easily reach the soil below, and even if they do, the unstable, shifting environment of rocks makes it nearly impossible for roots to establish themselves. The few plants that do manage to grow stay small and weak and don't pose any real threat to the structure. In the early days of railways, before engineers understood the importance of weed control, some lines had to employ workers whose entire job was pulling weeds from between the tracks. The vegetation would grow so thick during summer that it would actually start to lift the rails off the ties. Once they switched to deeper ballast beds, that problem disappeared entirely. The word ballast actually comes from the sea rather than from railways. Centuries ago, when empty wooden ships sailed to pick up cargo, they were too light to sail safely because without weight in the hold, they would bob around in the waves in a way that was unstable and dangerous. The hull would sit too high in the water, making the ship difficult to steer and vulnerable to capsizing in rough seas. Sailors solved this by filling the ship's hold with heavy stones that they called ballast, which kept the ship low in the water and stable during the voyage. The stones needed to be heavy enough to provide stability, but worthless enough that nobody cared about leaving them behind once the ship reached port to load paying cargo. When the ships arrived to pick up goods, they would dump these stones on the shore to make room in the hold, and piles of discarded ship ballast accumulated at every major port city until some ports had entire beaches made of ballast stones from ships around the world. Early railway engineers in the 1800s were looking for cheap, heavy material to stabilize their new tracks. And when they looked at these massive piles of free stones sitting at the docks, they realized they could use them for the same purpose on land. The ship's ballast became the foundation for train tracks, and the name transferred over with it. What started as dead weight tossed from sailing ships became the foundation of every railway line in the world. The rocks are so effective that the basic design hasn't changed in 200 years. Modern high-speed trains traveling at 300 kilometers per hour still ride on crushed stone arranged the same way as Victorian steam engines, and engineers have tried alternatives over the years but keep coming back to rocks. Concrete slabs seemed like an obvious improvement because they're solid and uniform and don't need replacement, and some urban metro systems use them because space is limited and maintenance windows are short. But concrete has two fundamental problems the rocks don't. First, it's rigid and transfers vibration directly into the ground and nearby buildings instead of absorbing it. Second, when concrete cracks under repeated stress, you can't just scoop out the broken section and pour in fresh material the way you can with rocks. Rocks can be adjusted, added, or removed easily. So if the track starts to settle unevenly, maintenance crews simply lift the rails and add more ballast underneath in a way that's impossible with a concrete slab. Even the latest magnetic levitation trains, which don't even touch the track while running, still need ballast underneath their guideways for the same structural reasons that conventional railways do. Fresh ballast is sharp and angular and does its job perfectly, but over years of use, the rocks start to break down. The constant pounding of trains slowly grinds the edges smooth, so the sharp angles that created all that friction begin to round off, and when this happens, the ballast loses its grip and the rocks start to shift under the track. Maintenance crews arrive with a machine called a ballast tamper that literally shakes the track and vibrates the rocks back into tight formation. The machine has hydraulic arms that lift the rails slightly, while pneumatic hammers pound the rocks underneath and force them back into an interlocked position. Eventually, the rocks become too smooth and need to be replaced entirely, so the old ballast gets scooped out and fresh, sharp stones get poured in. Some of that old ballast gets recycled and crushed down further for use in concrete or road construction, while some of it ends up as decorative gravel in gardens, so the rocks that carried trains for decades wind up in driveways and landscaping. The specifications for track ballast are surprisingly precise because railway engineers don't just dump any rocks under the tracks. They follow exact standards for size, shape and material that have been developed over nearly 2 centuries of experience. The rocks must be between 2 and 6 centimeters in diameter because too small and they won't create enough friction, while too large and they won't pack together properly. The stone must be hard, with granite and basalt being preferred because they resist crushing under the immense weight, while softer stones wear down too quickly. The shape matters because the rocks need to be angular but not so sharp that they cut through the wooden ties. The rocks must be clean as well because dust and fine particles fill in the gaps between stones and reduce drainage, so fresh ballast gets washed before it's laid down. Quality control is serious because every shipment of crushed stone gets tested for hardness, size distribution, and angularity before it's approved for use. A single kilometre of railway track sits on roughly 2,000 tons of crushed stone, and high-speed lines use even more because they need deeper ballast beds. The quarries that produce railway ballast are massive operations, and some of them are dedicated entirely to supplying railways with the specific type of stone they need. Different countries have developed their own variations on the basic ballast system, but the principle remains the same everywhere. In Japan, where earthquakes are a constant concern, the ballast beds are deeper and more carefully engineered because the rocks need to absorb not just the weight of the train, but also the sudden lateral shaking of seismic activity. In extremely cold climates like Siberia, engineers have to account for frost heave because when water in the ground freezes, it expands and pushes the tracks upward. So the ballast needs to be thick enough to act as a barrier between the frozen ground and the rails above. Desert railways face the opposite problem because blowing sand tries to bury the tracks, which means the ballast needs to be heavy enough that wind can't move it, and the rocks need to be large enough that sand doesn't fill the gaps. In each case, the solution is still crushed stone, just adapted to local conditions. The engineering might get more sophisticated, but it's still based on the same principle of sharp rocks packed together to spread weight, drain water, and lock the track in place. Modern sensors and monitoring systems can now detect when ballast is wearing out before it becomes a safety issue. Trains equipped with ground-penetrating radar scan the trackbed as they travel, and when the sensors detect settling or smoothing, maintenance gets scheduled before problems become serious. But even with all this technology, the basic process hasn't changed. Crews still dig out old ballast and pour in new rocks, while machines still tamp and compact the stones into place. A pile of carefully chosen crushed rocks does everything a railway needs. It's cheap to produce, easy to install, simple to maintain, and nearly impossible to break. And it works in every climate, on every terrain, under every type of train without requiring power or moving parts. The next time you see those jagged grey rocks beside a railway line, you'll know they aren't just random stones dumped there. They're a self-draining, weed-fighting, weight-bearing engineering solution that has kept the world moving for 200 years and started as garbage tossed off sailing ships. If you had to design a support system for train tracks from scratch, would you have thought of using loose rocks? Or would you have gone with something that seemed more solid and permanent? Leave your answer in the comments. If you enjoyed this, hit the like button and subscribe for more videos like this.